We are introducing basic diode concept. So a diode is a two-terminal device. Uh, if you please look at this picture, please look at this picture. This is the image. This is a photo of a diode, and it has two terminals, anode and cathode. Anode is the positive terminal, and anode is negative terminal, and it only allows current flows in one direction from anode to cathode. So this is the symbol. This is the symbol of a dial. And on top of it, it's a photo of a real dial. And comparing to a water system, if you look at the image on the right, a dial is equivalent to a flapper valve. So it has a flapper here. It only allows water to flow in one direction, and it doesn't allow water to go back. And we also call this flatter valve a check valve. So um, they, it has three regions when we apply voltage. So, so on the if you look at the picture in the middle, it is a characteristic diagram to describe the current flows through a dial and the voltage across the dial. So how can we get this picture? How can we get this graph? Um, the way that we get this graph is we connect this dial with a resistor and with with a battery or a voltage source. So we keep increasing the voltage from negative voltage to positive voltage, and then we try to use a current meter to measure the current. So we have this characteristic curve. And so if we apply a positive a positive voltage, just like what I draw here. This is this is positive, this is negative. So we apply a positive voltage to this dial, and at certain threshold, it will. So at certain threshold, the current increases largely, and the voltage across the dial remains the same. Later on, we will call this a knee voltage, and usually we use VR, a threshold. And if you apply negative voltage, so if you apply negative voltage to a dial, so it's equivalent to you apply a negative voltage. So this is positive, negative. Then you apply a negative voltage to this dial. We call it is functioning at reverse bias region. And you can notice that the current the current is negative, because this is the current here. It's a negative current, and its amplitude is very small. Okay, so if you draw the arrow like this, the negative IG means it's flowing backwards, but it's very small the comparing to the magnitude of current at this forward bias region. And if we keep increasing this negative voltage, it reaches the breakdown region. So we call this reverse breakdown. So where a high negative voltage triggers large reverse currents without damaging the device if heat is managed. So it doesn't damage the dial, but as long as it is at breakdown region, this negative current, which means the current in the reverse direction will also increase largely. So this directional control is widely used in applications like automotive systems to let alternator charge the battery while preventing reverse discharge when turned off. So it's very commonly used. So uh, we often, so previously on the previous slides, we show you the shape of this characteristic diagram to describe the voltage and current of a dial. And here, usually we we focus on small signal dial, and it is a primary choice for low to medium power circuits. In forward bias at room temperature, it's about 300 K. It's about 26 Celsius, 26 C. Current remains negligible until reaching a knee voltage. So that's what I said, knee voltage around zero point 0.6 to 0.7 volts, after which current increases rapidly. And also, this knee voltage, it will it will drop with the increase of temperature. So it's with each K, it decreases by 2 millivolts. So it can also serve as a temperature sensors in electronic thermometer. We only need to keep it a certain current. We make sure the current remains the same, and by this threshold voltage, and then we can try to relate to temperature. So in reverse bias, current stays minimal. It's about -1 nanoampere at 3000 K, but roughly doubles every 10K temperature rise. But so this figure is a little bit exaggerate. Actually, -1 nanoamp is very small. Okay. And usually the breakdown voltage and the amplitude of the breakdown voltage will be way larger than knee voltage. So if, for example, you look at this case, the knee voltage is zero point 0.6 volts, but the breakdown voltage is minus 100 volts. So this minimum breakdown voltage is a crucial circuit design specifications. We will introduce its application in the following sections. Okay, so this is the characteristic diagram of a rail dial. And so we have two ways. We have two ways to get this characteristic diagram. The first way is by measurement. As we previously says that we increase the voltage across the current and measure the uh, we 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 measure the we apply which we adjust the voltage across this diode and measure the current, and then we can draw this characteristic diagram. And the second way is we can use a mathematical equation to approximate the curve. So this mathematical equation is called Shockley equation. So it models the theoretical relationship between current and voltage in a junction diode. So it's an exponential function. So exponential VD is the voltage across the diode. ID is the current across the dial. And and IS is the saturation current, and it's about 10 to the power of minus 14 ampere at room temperature. It doubles every 5K rise in silicon. Okay, N is the emission coefficient, is usually between 1 and 2, and VT is the thermal voltage, usually, and KT is some coefficients, and T is the temperature, Q is the magnitude of the electrical charge of an electron, but usually it will be given. So let's assume that it is 0.026 volts at 300 K. Okay, this is VT. So by this equation, we are able to approximate the curve, uh, but only for forward bias, which means only for this. This is VD. This is ID. This is ID. Only for only to describe this. Okay. So this equation accurately models forward currents between 0.01 milliampere and 10 milliampere, and typically with n equals to 1. So within this range, this model can approximate this curve accurately. So if there are sufficient forward bias, for example, is VD is large. So if VD is large and much way larger than MVT, then this number will be very large. And then because it's exponential, so it will be way larger than 1. So we can ignore this minus 1. So the relationship between ID, the current and voltage of a dial can be approximated by this equation. And you don't need to memorize this because if it's in the exam, this formula will always be given. Okay, you just need to know that this simplified formula describe this curve. Okay, and well, because simplified theoretical assumptions ignore certain phenomena, the equation becomes inaccurate at extreme current levels, underestimates reverse bias leakage, and fails to account for reverse breakdown. So it didn't consider reverse breakdown, and you can notice if VD is minus, this will be very small, and it will have a very small, if minus, it will have the curve will be like this. So it doesn't consider for reverse breakdown. Okay, so well, but this is how we approximate this characteristic diagram of a dial when it's under forward bias. So remember, Sharkey equation is for forward bias. Okay, next. All right. So we will work on two exercise. So I will show you how to calculate. So first, at the temperature of 300 K, a certain junction diode has the current ID equals 0.1 milliampere, and VD is 0.6 volts. Assume that N is unity and use VT equals 0.026 volts find the value of the saturation current Is. Then compute the diode currents at VD equals 0.65 volts and at 0.7 volts. So I may just calculate. I may just calculate one condition. So first of all, we need to write down this simplified equation. Okay, so we write down this. ID is Is equals Is ex exponential VD and VT. Okay, because in this case, VD is 0.65 uh, compared to NVT is large enough. So we just ignore the -1 and then we plug in all the numbers. So ID is 0.1 milliampere, so times 10 to the power 3. This is Is, and this is exponential. This is 0.6 volts, and then N is 1, and VT is 0.026. Well, you can easily calculate Is. So uh, Is is ID 0.1 times 10 to the power minus 3. This is exponential 0.6, 0.0226, which is, I believe the answer should be right because it's very easy. Minus 3 divided by exponential 0.6 divided by 0.026. Wow, it's really small. Okay, so Is equals 9.5 times 10 to the power of minus 15 ampere. Actually, the answer is on the textbook already. So I believe you should be able to calculate this on your own. Okay. And then we look at exercise 9.2. Consider a diode under forward bias so that the approximate form of the Shockley equation applies. Assume that Vt is 0.026 volts and N is 1. So A, by what increment must Vd increases to double the current? B, to increase the current by a factor of 10. So at this condition, what increment must Vd increases? So I just solve A for you. Um, but you are always welcome to do it on your own. So this is example 9.1. This is example 9.2. And same thing, we look, this is ID, we write down this simplified Shockley equation. Exponential, this is VD, this is NVT. So, so we want to double the current. So we double the current to ID equals Is exponential. This is VD prime and VT. Okay, so we have two equations. And then we have equation 1 and equation 2. So for two equations, so we make it 1 over 2. So we divide these two equations. So ID, this is 2ID equals IS, this is exponential VD and VT. This is IS exponential. This is VD prime and VT. So cross, 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 cross. And so we have this 1 over 2 equals exponential. This will be VD minus VD prime divided by MVT. Okay, so you should know this, right? So if you have exponential 3 divided by exponential 5, it will be exponential 3 minus 5 is exponential minus 2. Okay, so we divide it by this power, and then we can take natural log. So we take natural log on both sides So we have this natural log 1 over 2, and this is VD minus VD prime and VT. Okay, so VD minus VD prime, and then N is 1, and VT is 0.026. So you have VD minus VD prime equals natural log 1 over 2. So you have natural log 0.5 times 0.026 minus 0.018. So which means VD prime minus VD equals 0.018. And so it needs to increase by 0.018 volt. So you need to, so for the voltage applies to this diode in order to make the current increases by 2 volt, you need to increase it to by the increase of the voltage must be 0.0180 volt. It equals 18 millivolts. Okay, so yeah, that's how we solve it. And one more thing I want to talk about, because if you look at the answer of exercise 9.1, so at VD equals 0.65 volts, its current is very small, 9.5 times 10 to the power of minus 15. But if you increase to 0.7 volt, so this is um, no, this is its saturation current. So if you look at VD here, find value saturation current, computer diode current. Oh, I didn't finish exercise 9.1. So yeah, we haven't finished it because we only have saturation current. So, and then we need to calculate ID equals IS exponential in VD is 0.65, and then this is 0.026. So the answer, if you plug in the IS and let me write down all the numbers. So ID equals 9.5 times 10 to the power of minus 15. And then this is exponential VD 0.65. And then this is 0.026. I will just write down the answer. The answer should be 0.684 milliamp. And then another IT at 0.7 volts is how we calculate. This is exponential is 0.726, which is 4.68 milliamp. So we know that this knee voltage is around 0.7 volt. So right, so when the voltage applied to this diode, as long as it is larger than this knee voltage, the current starts increasing. But if the voltage is lower than this knee voltage, or we call it threshold voltage, the current is very small. Okay, so so you can use this Shockley equation to describe the forward bias of a dial. All right, so this is the exercise to let you be familiar with this equation. Okay. In addition, so we introduce we've introduced the characteristic equation, and it can be received by either measuring the voltage and current of a dial, or it can be approximated by a mathematical equation. And here we are introducing uh, the way to analyze the circuit if a diode is in the circuit. So uh, and then of course the the relationship between the voltage and current of a diode is a nonlinear function. So what is linear? If the voltage and current, so if so we have Ohm's law. Almost Ohm is V divided by R. So if this is V, this is I, then the slope is 1 over R, right? Yeah, it's 1 over R. And then um, this is linear. We call this linear function. Then this is the relationship of the voltage and current of a resistor, right? So it is Ohm's law. I believe you know. Of course you know. You learned electrical engineering. So this is Ohm's law. All right. But this is nonlinear. So if we have a diode in a circuit, we need to uh, there are several ways to analyze it. The so the first we are talking about is we try to solve this ID and VD graphically, which means uh, we try to locate the values on a graphic, like the graphic on the slides. Okay, so how do we start? Uh, the way is called load line analysis. And first, we need to build a load line. What is a load line? A load line is this equation. This equation is built by KVL, and it needs no matter what kind of electric element in the loop, it always needs to be satisfied. So how does it come from? So by KVL, so the KVL says that the summation of the voltage um, of the element within a loop is zero. So for me, I always start at bottom left corner, and when I run clockwisely when I meet a certain element, when I meet its negative terminal, and I say minus. So first is minus VSS, and because we assume the current flows in a clockwise direction, so for this, for because the resistor always consume energy, so the current flows into its positive terminal. So here is positive, this is negative, and the voltage across this resistor is R times ID. So I meet this resistor, so it's plus R times ID, and then I meet I meet this diode and it's plus minus, so plus VD. So I go back to the same note. This is KVL, Kirchhoff voltage law, and equals zero. So by some adjustment, you have VSS equals RID plus VD. So, um, so if VSS is given, R is given, usually its voltage source will be given, and the resistance is also given. So you have this equation to describe, you have this equation. This is called load line to describe the current and voltage of a diode. And then we draw here. We draw at this line. So before we draw it on this VDIG plot, we need to identify two crucial points. The first point, point A, is when ID is zero. When ID is zero, it's a horizontal line. When ID is zero, you put zero into ID, you have VD equals VSS. So this is point A, or it is written. So this is point A. You have point A, and then we identify another point, which means we make VD zero. VD is zero, which means it's the intersection of this horizontal, it's a vertical line. So if you put VD zero here, you have ID equals VSS divided by R. So this is point B. So we have this point. So we identified these 2 points, and then we can draw the load line. And then by by the measurement, we have this diode characteristic curve. So the intersection of this diode characteristic curve and this load line will be the operating points. And then we can find out this is VD and ID in this circuit. Okay, so the operating point, also called Q point. So Q point of the circuit is found at the intersection of the load line and the nonlinear diode characteristic curve, which represents the simultaneous solution for diode voltage VD and current ID. Okay, so this is one way to analyze the diode current and voltage when it is in a circuit. Okay. Okay, and then we have two examples, and so I can show you how to solve it. So if the circuit of figure 9.5 has, well, this is show 9.7. Okay, yeah, this is the same figure. Has VSS equals to 2 volts, R equals 1K ohm, and a dial with the characteristic shown in this figure 9.7, find the dial voltage and current at the operating point. So, oh, we have to draw, let me draw 9.5. Let me draw 9.5 here. So, so you need to have this. So they just say it is the same circuit. So we have R, and then we have a dial, and you need to pay attention to a direction. So we always define the bottom of triangle is anode, and the point of the triangle is cathode. And then so this is positive, negative, VSS. So it only allows, so we only consider the forward bias region. So for forward bias region, it only allows a current flows from anode to cathode. So this is ID. So once we define the direction of current, then we know this positive, negative, and the voltage across this resistor is RID. So this is figure 9.5. Okay, and then you need to you need to you need to define the equation of KVL. So you have minus VSS plus RID plus this is VD, okay, plus VD equals 0. And then so you have this VSS equals RID plus VD. First, you need to have this equation, and then we identify point A and point B. So when ID is 0, we have VSS equals VD, which is we have VD is equal we have VD equals VSS, which is 2 volts. And then when VD is 0, we have ID equals VSS divided by R, which is 2 divided by R1K is 2 milliampere. So, uh, so, so ID is 0 and VD is 2. So this is point A, and then VD is 0 and ID is 2 milliampere. So this is point B. So we can draw the low line, and the intersection if it's in the exam, this figure will be, the scale will be more accurate, so you can find out roughly at this settings the VD is 0.7 and ID is 1.3. Okay, so graphically we solved it. This is a graphical solution. Graphical solution. Okay, and then we look at example 2. If VSS equals 10 volts and R equals 10K ohm. Well, basically they are the same procedure, but this example 9.2 is a little bit tricky. So same thing, we write this KVL equation, RID plus VD, but right now VSS equals to 10 and R equals 10K ohm. So when ID equals 0 and VD equals what? VD equals to 10 volts. And then when VD equals 0, and ID equals VSS divided by R, which is VS is 10, it's 10K. This is 1 milliampere. So for this point is this easy. So for this point is here. ID equals 0 and VD is 0 and ID is 1 milliampere. But for this point, ID is 0, but VD equals to 10. But VD here, it, it, it has, for 10, it might be way outside the graph, way outside this picture. So, but we can, it's not there. So in this case, we can only assume that we locate a scale, maybe on the plot, and say we try to find point D. So to find point D, we say um, VD is 2 because it is within the scale. So VD is 2, ID is when VD is 2, and when VD is 2 volts, and ID will be VSS minus VD divided by R. So VS is 10 divided by 2, minus 2 divided by 10K is 0.8 milliampere. So we locate point D. Point D is 2 and ID is 0.8 milliampere. So we can still drawing a long line and then find out the intersection. Intersection. So this is the VD we need to calculate. This is the ID we need to calculate. So example 9.2, although their procedures are the same, but example 9.2, it just means it just teach you when when one point is out of the scale of this diagram, how you can still try to solve the problem. Okay, and right, let's look at the next page. Exercise 9.3. Find the operating points for the circuit of figure 9.5. It's the same figure. So it's the same circuit diagram. So let me draw it really quickly here because they are the same. VSS, positive, negative. This is R, this is ID, this is VD. Okay, so this is the same, very simple circuit. This is VD. And then, okay, it gives you the characteristic curve of this dial, and it asks you to find out a. So you're given voltage source and resistance, and so it asks you to find out the ID and VD. Uh, I just use I just solve A, and please practice B and C on your own. So we write down this equation. Well, you are very familiar with this, so I believe we don't need to do this start all over again by KVL. So we have this, and then so we locate we need to draw the low line. So for ID equals 0, then VD equals VSS equals 2 volts. Okay, and for VD is 0, And we have ID equals VSS divided by R, which is 2 divided by 100, which is 0.02, right? 0.02, which is 20, 20 MA, milliampere. Okay, so we locate these 2 points on the plot. So first is ID equals 0, and this is and then VD is 2 is here is points, and another is VD 0 and ID is 20 milliamp. So I need a ruler. Hopefully I can make it straight. Okay, let me try to draw this. Perfect. It doesn't look straight, but it should be fine. And so we locate points. This is our operating point. This Q point. And then so we try to graphically. Oh, wait. Uh, my bad. So we try to. Okay. Try to make a line. Oh no. Okay, it's really hard for me to draw it straight. All right, approximately. Approximately. So here, the value here should be about here, about 1.1 volts, and the current is about 9 milliampere. So is it the same with the solutions? Let me check. Okay, it's about, yeah, it's VDQ. VDQ means the VD at the operating point is 1.1 volts, and this IDQ, it means the current at the operating point is 9 milliamp. So this is the solution of A. And I want you to work on the solution of B and C on your own. And we finish this section, and then we will continue to talk about the remaining sections next time. All right.